Classical gravity is the theory of gravity that was developed by Isaac Newton in the 17th century and refined by Albert Einstein in the 20th century. It describes how massive objects attract each other by warping the fabric of space and time, and how their motions are determined by the curvature of this fabric. Newton's theory of gravity, also known as Newtonian gravity or universal gravitation, is based on the idea that every object with mass exerts a gravitational force on every other object, proportional to their masses and inversely proportional to the square of the distance between them. The gravitational force is given by the formula F equals gr2 m1 m2, where F is the force, g is the gravitational constant, m1 and m2 are the masses of the objects, and r is the distance between them. Newton's theory can explain many phenomena, such as the orbits of planets, the tides, and the motion of projectiles. However, it cannot account for some effects, such as the precession of Mercury's orbit, the bending of light by gravity, and the gravitational redshift of light. Einstein's theory of gravity, also known as general relativity or relativistic gravity, is based on the idea that gravity is not a force, but a consequence of the geometry of space and time. According to Einstein, space and time are not fixed and absolute, but dynamic and relative. They can be stretched, squeezed, twisted, and bent by the presence and motion of matter and energy. The curvature of space and time affects the paths of objects in light, creating the illusion of a gravitational force. Einstein's theory can explain all the phenomena that Newton's theory can, as well as the ones that it cannot. The curvature of space and time is given by the equation g equals agt, where g is the Einstein tensor, which measures the curvature of space and time, g is the gravitational constant, and t is the stress-energy tensor, which measures the distribution and flow of matter and energy. Einstein's theory is more complex and mathematically challenging than Newton's theory, but it is also more accurate and elegant. Classical gravity is a remarkable achievement of human intellect and imagination, but it is not the final word on the nature of gravity. There are still many open questions and challenges, such as the origin and fate of the universe, the nature of black holes and singularities, the existence and properties of gravitational waves, and the compatibility of gravity with quantum mechanics. These questions require new theories and experiments, which may reveal new aspects and dimensions of gravity that we have not yet imagined. Relativistic gravity is the concept of gravity that emerges from the theory of general relativity, which is the geometric theory of gravitation published by Albert Einstein in 1915. According to general relativity, gravity is not a force, but a manifestation of the curvature of space and time caused by the presence and motion of matter and energy. The curvature of space and time affects the paths of objects in light, creating the illusion of a gravitational force. Einstein arrived at the theory of general relativity after realizing that his previous theory of special relativity, which describes the physics of inertial frames of reference, could not account for gravity or acceleration. He was inspired by the principle of equivalence, which states that there is no way to distinguish between a gravitational field and a uniformly accelerated frame of reference. He also realized that gravity affects not only matter, but also light and time. He then sought to find a mathematical framework that could describe the laws of physics in any coordinate system, regardless of its state of motion or gravity. Einstein's discovery of general relativity was not a single event, but a long and arduous process that involved many trials and errors, collaborations and controversies, and revisions and refinements. He began working on the problem of gravity in 1907, and published his first paper on the topic in 1908. He then developed the concept of the metric tensor, which encodes the geometry of space and time, and the notion of the covariant derivative, which allows for the calculation of physical quantities in curved spacetime. He also introduced the concept of the stress-energy tensor, which measures the distribution and flow of matter and energy. In 1912, Einstein's friend and mathematician Marcel Grossmann introduced him to the tensor analyses of Bernhard Riemann, Tullio Levi-Civita, and Gregorio Ricci-Cabastro, which provided him with the tools to express the laws of physics in a generally covariant way. He also collaborated with another mathematician, David Hilbert, who helped him to formulate the variational principle for the theory. In 1913, he published the 12th outline paper with Grossmann, which contained a preliminary version of the theory, but was later shown to be incorrect. In 1915, Einstein visited Hilbert in Göttingen, and Hilbert convinced him that the goal of a fully general relativistic theory was achievable, something Einstein had nearly given up on. Einstein returned to work, and by November, he had found the correct field equations, which relayed the curvature of space and time to the stress-energy tensor. He presented his results in 4 papers to the Prussian Academy of Sciences, and in the 3rd paper, he used general relativity to explain the anomalous precession of the perihelion of Mercury, which had puzzled astronomers for decades. He also predicted the bending of light by gravity, which was later confirmed by the observation of the solar eclipse in 1919. Einstein's theory of general relativity is one of the greatest achievements of human intellect and imagination, and has revolutionized our understanding of the universe. It has also led to many fascinating and profound predictions and discoveries, such as gravitational waves, gravitational lensing, gravitational time dilation, black holes, and the Big Bang. However, it is not the final word on the nature of gravity, as there are still many open questions and challenges, such as the origin and fate of the universe, the nature of singularities, the existence of dark matter and dark energy, and the compatibility of gravity with quantum mechanics. These questions require new theories and experiments, which may reveal new aspects and dimensions of gravity that we have not yet imagined. Einstein's field equations are the core of his theory of general relativity, which describes how gravity is a result of the curvature of space and time. The equations relate the geometry of space and time, expressed by the metric tensor, to the distribution of matter and energy, expressed by the stress-energy tensor. The equations are G equals mgt, where G is the Einstein tensor, which measures the curvature of space and time, G is the gravitational constant, and T is the stress-energy tensor, which measures the density and flow of matter and energy. The equations are a system of 10 nonlinear partial differential equations that can be solved for the metric tensor, given the stress-energy tensor. The solutions of the Einstein field equations are metrics of spacetimes that describe the gravitational effects of different sources of matter and energy. Some of the most famous and important solutions are the Schwarzschild solution, which describes the spacetime outside a spherically symmetric and on-rotating mass, such as a star or black hole. It predicts the existence of event horizons and gravitational redshifts. The Kerr solution, which describes the spacetime outside a rotating mass, such as a spinning black hole. It predicts the existence of gas spheres and frame tracking effects. The Friedmann-Lemaitre-Robertson-Walker (FLRW) solution, which describes the spacetime of a homogeneous and isotropic universe. It predicts the expansion of the universe and the possibility of a Big Bang or a Big Crunch. The de Sitter solution, which describes the spacetime of a vacuum with a positive cosmological constant. It predicts the existence of a cosmic horizon and an exponential expansion of the universe. The anti-de Sitter solution, which describes the spacetime of a vacuum with a negative cosmological constant. It predicts the existence of a time-light boundary and a negative curvature of the universe. These are some of the exact solutions of the Einstein field equations, which can be found under simplifying assumptions such as symmetry or vacuum. There are also many other exact solutions, as well as approximate solutions and numerical solutions, which can be used to model more realistic and complex situations. Solving the Einstein field equations is a challenging and active area of research in mathematical physics and cosmology. Quantizing gravity is the problem of finding a theory that can describe the quantum behavior of the gravitational field, which is currently understood by the classical theory of general relativity. There are several approaches to this problem, but none of them are universally accepted or experimentally verified. Here are some of the main ideas and challenges of quantizing gravity. One approach is to treat gravity as a quantum field, similar to the other fundamental forces of nature. This means that gravity would be mediated by particles called gravitons, which would carry the gravitational interaction between other particles. However, this approach leads to mathematical inconsistencies and infinities, known as unnormalizability, which make the theory incompatible with observations and measurements. To avoid these problems, some physicists propose to modify the quantum field theory of gravity by introducing extra dimensions, supersymmetry, or higher-order terms in the equations. These modifications are often motivated by string theory, which is a framework that unifies all the forces in particles by describing them as vibrations of tiny strings in a 10-dimensional spacetime. String theory is one of the most popular and promising candidates for a quantum theory of gravity, but it is also very complex and difficult to test experimentally. Another approach is to treat gravity as a property of spacetime itself, rather than a separate force. This means that spacetime will be composed of discrete units or quanta, which would have quantum properties such as uncertainty and entanglement. These quanta of spacetime would form the fabric of reality, and their interactions would give rise to gravity and other phenomena. However, this approach faces the challenge of finding a consistent and coherent way to define and measure these quanta, and to explain how they relate to the continuum description of spacetime given by general relativity. Some examples of this approach are loop quantum gravity, which uses loops and networks of quantum states to describe the geometry of spacetime, and causal dynamical triangulation, which uses simplices and triangulations to model evolution of spacetime. These theories are less ambitious than string theory, as they do not attempt to unify all the forces in particles, but they are more focused on the quantum aspects of gravity. A third approach is to treat gravity as an emergent phenomenon, rather than a fundamental one. This means that gravity would not be a basic feature of nature, but a result of the collective behavior of other entities or systems. For example, some physicists suggest that gravity could emerge from the thermodynamics of information, or from the entropic forces of quantum bits, or from the holographic principle, which states that the information content of a region of space can be encoded on its boundary. These ideas are inspired by the discovery of deep connections between gravity, quantum mechanics, and thermodynamics, especially in the context of black holes and cosmology. However, this approach faces the challenge of explaining how the emergent gravity can reproduce the precise and elegant predictions of general relativity, and how it can be compatible with the quantum nature of the other forces and particles. Quantizing gravity is one of the most profound and difficult problems in physics, as it requires a radical revision of our understanding of reality. It also has important implications for the origin and fate of the universe, the nature of black holes and singularities, the existence and properties of gravitational waves, and the compatibility of gravity with quantum mechanics. These questions require new theories and experiments, which may reveal new aspects and dimensions of gravity that we have not yet imagined. The role of gravity at the beginning of time is one of the most intriguing and challenging questions in physics and cosmology. According to the standard model of cosmology, the universe began with a Big Bang, a state of extremely high density and temperature, where the laws of physics as we know them break down. Gravity, along with the other fundamental forces, emerged from this primordial state, and played a crucial role in shaping the evolution and structure of the universe. One of the main puzzles of the Big Bang theory is how the universe became so smooth and homogeneous on large scales, despite the initial fluctuations and irregularities. A possible solution to this puzzle is the idea of cosmic inflation, which proposes that the universe underwent a brief period of exponential expansion, driven by the potential energy of a new quantum field, called the inflaton. This rapid expansion would have smoothed out the initial conditions and stretched the quantum fluctuations to cosmic scales, creating the seeds of the large-scale structures we observe today. Gravity, as described by Einstein's general theory of relativity, is essential for inflation to work, as it allows for the possibility of repulsive gravitational force, generated by the negative pressure of the inflaton field. Another puzzle of the Big Bang theory is how the universe became so rich and diverse in matter and energy, despite the apparent symmetry and simplicity of the fundamental laws. A possible solution to this puzzle is the idea of symmetry breaking, which proposes that the universe underwent a series of phase transitions, analogous to the freezing of water or the magnetization of iron. During these phase transitions, the universe spontaneously chose a lower energy state, and some of the symmetries of the fundamental forces were broken, giving rise to different types of particles and interactions. Gravity, as the weakest of the four forces, played a minor role in these phase transitions, but it was crucial for the formation and stability of the cosmic structures, such as galaxies, stars, and planets, that resulted from the gravitational collapse of the primordial matter. A third puzzle of the Big Bang theory is how the universe became so complex and dynamic, despite the apparent tendency of physical systems to reach a state of equilibrium and entropy. A possible solution to this puzzle is the idea of chaos and emergence, which proposes that the universe exhibits an nonlinear and unpredictable behavior, sensitive to initial conditions and feedback mechanisms. During the evolution of the universe, new levels of organization and phenomena emerged from the interactions of simpler components, such as atoms, molecules, cells, organisms, and civilizations. Gravity, as the most universal and long-range force, played a major role in creating and maintaining the conditions for chaos and emergence, such as the formation of stars and planets, the origin and evolution of life, and the development and diversity of intelligence. The role of gravity at the beginning of time is not fully understood, as there are still many gaps and inconsistencies in our current theories and observations. For example, we do not know what caused the inflationary epoch, or what is the nature of the inflaton field. We do not know how to reconcile the quantum theory of the other forces with the classical theory of gravity, or what is the quantum behavior of gravity at the Planck scale. We do not know what happened before the Big Bang, or if there's a multiverse with different laws of physics. Goodbye.